All right, so we're at part two of problem solving with quadratics. I do want to revisit something real quick from the previous example. If you remember, I said that, well, this wasn't here before, but we came up with a solution that the dimensions of the original dimensions of the tin plate was 8 plus root 30 centimeters by 8 plus root 30 centimeters. Well, no one's going to give that dimension. What we should have done, or what I should have done, is put 8 plus root 30 in the calculator and then give the answer to three significant figures per IB guidelines, and that would round to 13.5 centimeters by 13.5 centimeters. So sorry about that. On to our next problem. Okay, so we have is it possible to bend a 12 centimeter length of wire to form the perpendicular sides of a right angled triangle with area 20 square centimeters? And I don't particularly like the way they worded this question, but we're kind of stuck with it. But here's what they mean. They're only talking about the sides of a right triangle. So, we have this, and then what they're saying is those are the only two sides of the triangle that are going to be formed using the wire. And then we have to imagine that it's an actual triangle. Okay, so there's like the hypotenuse is imaginary. It is a right triangle. And its area would be 20. So the question is, would a piece of wire 12 centimeters in length be able to accomplish this? And again, you're just bending this wire to form this right angle that would be the legs of, I guess, what we're going to think of as an imaginary right triangle. Okay. So immediately I'm going to label this entire length as 12 centimeters. Okay. And I know the question is this enough? Is there any way I could bend this so the area of a right triangle would be 20? Well, how do you find the area of a triangle? Well, the area of a triangle is equal to the base times the height divided by 2. Okay? And we know the target here is 20. So 20 is going to have to equal base times height over 2. So we have to get some sort of representation for base and height based on what we know. And here is a common strategy or a common way to deal with a known length and then to have to break it up. If I name from here to here, I just randomly pick that point, it doesn't matter. But if I call this x and the entire length is 12 centimeters, then the rest of the length from here to here has to be 12 minus x. And sometimes people have a hard time realizing that. Well, let's put a number in it. Let's say we know that this was 4. In other words, let's say we knew that from here to here was 4. Well, what would be the length from here to here? I don't think any of you would hesitate and say, oh, well, that's 8, Mr. B. Well, of course it is, but how about if we wrote 8 like this? Isn't it just 12 minus 4? 12 minus 4 is 8. Well, if this is x, then this length is 12 minus x. So that is a common method, a common way to use a variable to when it's involved with one length or something along those lines. If it's you let part of it be x, then the other part is 12 minus x or whatever the length may be. So if I bend this, then that would make this x, my height, and my base 12 minus x. Okay. Well, now I'm going to move this guy over here to give myself a little more room. 20 equals the base, so that would be 12 minus x times the height, x, all divided by 2. So I replace the b base with 12 minus x and the height with with x. And if I multiply both sides by 2, I get 40 equals Kapow theorem, 12 minus x times x, or 40 equals 12x minus x squared. And I'm going to move all these guys over here, set it equal to 0. So adding x squared, subtracting 12x, leaving 40 on the left side becomes 0. Now let's go back to the original question. Is it possible? Okay, is it possible? It doesn't say what are the lengths of the sides of these imaginary right triangles. It says, is it possible? Well, we have represented this entire situation with these equations here, and x does represent the height of the triangle, and 12 minus x is the base. So what we're really asking now, algebraically, is there a solution to this quadratic? Well, if there is a solution, then the discriminant must be greater than 0 or equal to 0. If there's not a solution, then the discriminant is less than 0. And that's all we have to know. Is there a solution? Not what's the solution, is there one? So all it boils down to is our good buddy delta, which is equal to b squared minus 4ac. And we just need to find out if this cowboy is positive, negative, or zero. So here we go. That's going to be 144, negative 12 squared, minus 4 times positive 1 times 40. So delta, I already know the answer, I hope you do too, 144 minus 160. That is going to be a negative number, negative 16, I believe. I don't care about the 16. What I care about is the negative, and that implies, that tells me that, is it possible? No, it is not possible, would be my answer. And anytime you're asked something like that, you should answer in a complete sentence. So it's not possible, given all of this information, given all these parameters, it is not possible to form a triangle that has an area of 20. Okay? All right, so I'm going to end that there, and I am going to give one more example in another video if you want to watch it. Just more practice, and we'll see you then. Thanks. Bye.